Download this code from codegive.com, link in the description below. Round Robin Scheduling Explained, a detailed tutorial, Part 1. Round Robin, RR, scheduling is a preemptive, time-sharing CPU scheduling algorithm. It assigns each process a fixed time unit, called a time quantum or time slice. If a process is not completed within its time quantum, it is preempted and moved to the back of the ready queue. This ensures that all processes get a chance to execute within a reasonable time frame, preventing starvation and promoting fairness. This tutorial will cover the following aspects of round-robin scheduling. Part 1, this part. 1. Concept overview * a deeper understanding of the algorithm and its benefits. 2. Key parameters * defining and explaining the time quantum. 3. Algorithm implementation * breaking down the algorithm into logical steps. 4. Simple example walkthrough * manually simulating RR with a few processes. 5. C++ code implementation, a basic implementation in C++ demonstrating the core logic. Part 2, future part. 6. Code optimization and refinement * improving the C++ code for clarity and efficiency. 7. Handling arrival times * adding complexity to the code to handle processes arriving at different times. 8. Calculating performance metrics * calculating average waiting time and turnaround time. 9. Handling I/O burst * discussing how RR deals with I/O bound processes. 10. Advantages and disadvantages * a complete overview of RR's pros and cons. Let's begin with part 1. 1. Concept overview. Imagine a classroom where students have to share a computer. Instead of letting one student use the computer until they're finished, like first come, first served, round robin gives each student a small, fixed amount of time, example 5 minutes. If the student isn't done after 5 minutes, they have to get back in line and wait for their next turn. This is essentially what round robin does with processes competing for CPU time. The CPU allocates a time quantum to each process in the ready queue. If a process completes its execution within the quantum, it's removed from the queue. If it doesn't, it's preempted and moved to the back of the queue, waiting for its next turn. The main goals of round robin are fairness * every process gets a chance to run, preventing long delays or starvation. Responsiveness * users experience faster response times because short processes complete quickly and longer processes are not allowed to monopolize the CPU. Simplicity * the algorithm is relatively simple to implement and understand. 2. Key parameters, time quantum. The most crucial parameter in round robin is the time quantum, Q. It represents the amount of time each process is allowed to run before being preempted. The choice of the time quantum is critical and directly affects the performance of the algorithm. Small time quantum * pros * improved responsiveness. Short processes can complete quickly. Cons * increased context switching overhead. Context switching involves saving the state of the current process and loading the state of the next process, which takes time. If the quantum is too small, the CPU spends more time switching between processes than actually executing them, leading to reduced CPU utilization. Large time quantum * pros * reduced context switching overhead. Approaches first come, first served, FCFS, behavior. Cons * reduced responsiveness. Long processes can hog the CPU, leading to longer waiting times for other processes. It can also become less fair. Ideally, the time quantum should be chosen such that Asterisk it's long enough to allow most processes to complete their CPU burst within a single quantum. Asterisk it's short enough to provide good responsiveness and fairness. The optimal value often depends on the characteristics of the processes being scheduled and the hardware configuration. A good rule of thumb is to choose a quantum that is larger than the typical context switching time but significantly smaller than the typical CPU burst of processes. 3. Algorithm implementation. Here's a breakdown of the round-robin scheduling algorithm. 1. Initialization asterisk. Asterisk create a ready queue to hold processes waiting to execute. Asterisk determine the time quantum, Q. Asterisk for each process. Asterisk store the process ID, arrival time, if applicable, CPU burst time, remaining time, waiting time, and turnaround time. 2. Main loop asterisk. Asterisk while the ready queue is not empty or there are processes that haven't arrived yet. Asterisk add arrived processes asterisk check if any processes have arrived at the current time and add them to the ready queue. Asterisk process execution asterisk. Asterisk if the ready queue is not empty. Asterisk select the process at the front of the ready queue. Asterisk execute the process for either the time quantum, Q, or its remaining time, whichever is smaller. Asterisk update the remaining time of the process. Asterisk update the waiting time for all processes currently in the ready queue. Asterisk if the process completes, remaining time becomes 0. Asterisk remove it from the ready queue. Asterisk calculate its turnaround time, completion time, arrival time. Asterisk else, process is preempted. Asterisk move the process to the back of the ready queue. Asterisk increment time asterisk increment the current time by the amount of time the process was executed for. 3. Performance metrics asterisk. Asterisk calculate the average waiting time, sum of all waiting time / number of processes. Asterisk calculate the average turnaround time, sum of all turnaround time / number of processes. 4. Simple example walkthrough. Let's walk through a simple example to illustrate how round-robin works. Assume we have 3 processes, P1, P2, and P3, with the following CPU burst times. Asterisk P1, 24 units. Asterisk P2, 3 units. Asterisk P3, 3 units. Let's set the time quantum, Q, to 4 units. Assume all processes arrive at time 0. Time process executing P1 remaining P2 remaining P3 remaining ready Q. Dash 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 dash. 0 P1 24 3 3 P1, P2, P3. 4 P2 23 3 P2, P3, P1. 7 P3 20 0 3 P3, P1. 10 P1 20 0 0 P1. 14 P1 16 0 0 P1. 18 P1 12 0 0 P1. 22 P1 8 0 0 P1. 26 P1 4 0 0 P1. 30 P1 0 0 0. Process completion times asterisk. Asterisk P1, 30. Asterisk P2, 7. Asterisk P3, 10. Turnaround times, completion time, arrival time. Asterisk P1, 30 to 0 equals 30. Asterisk P2, 7 to 0 equals 7. Asterisk P3, 10 to 0 equals 10. Waiting times, turnaround time, burst time. Asterisk P1, 30 to 24 equals 6. Asterisk P2, 7 to 3 equals 4. Asterisk P3, 10 to 3 equals 7. Average turnaround time asterisk, 30 plus 7 plus 10, slash 3 equals 15.67. Average waiting time asterisk, 6 plus 4 plus 7, slash 3 equals 5.67. 5. C++ code implementation, basic. Here's a basic C++ implementation of round-robin scheduling. This implementation assumes all processes arrive at time 0. We'll expand on this in part 2. Explanation of the code asterisk. One process struct asterisk defines a structure to represent a process, holding its ID, burst time, remaining time, waiting time, and turnaround time. 2 main, function asterisk. Asterisk takes the number of processes, n, and the time quantum, as input from the user. Asterisk creates a vector of process objects to store the processes. The burst time for each process is also read from the user. Asterisk creates a queue called ready queue of process asterisk, pointers to process objects. This represents the ready queue. Asterisk adds all processes to the ready queue initially. Asterisk initializes current time to 0. 3 while loop asterisk. This is the main loop that simulates the execution of processes. The loop continues until the ready queue is empty. Asterisk dequeue asterisk removes the process at the front of the ready queue. Asterisk execute time asterisk determines the amount of time the current process should execute, which is the minimum of quantum and current process dash remaining time. Asterisk output asterisk prints a message showing which process is executing and for how long. Asterisk current time update asterisk updates the current time by execute time. Asterisk remaining time update asterisk decreases the remaining time of the current process. Asterisk waiting time update asterisk increment waiting time of the processes in the queue. We iterate through the queue adding the current execute time to their waiting time. Asterisk process completion asterisk if current process dash remaining time is 0, the process has completed. Its turnaround time is calculated, and a completion message is printed. Asterisk preemption asterisk if current process dash remaining time is greater than 0, the process is preempted and added back to the end of the ready queue. For performance metrics calculation asterisk after the while loop finishes, all processes are completed, the code calculates the average waiting time and average turnaround time. 5 output asterisk the average waiting time and average turnaround time are printed to the console. How to compile and run the code asterisk. 1 save the code as a .cpp file, example round_robin.cpp. 2 open a terminal or command prompt. 3 compile the code using a C++ compiler, like G++. 4 run the executable. The program will prompt you to enter the number of processes, the time quantum, and the burst time for each process. It will then simulate round-robin scheduling and print the execution order, completion times, average waiting time, and average turnaround time. This concludes part 1 of the round-robin scheduling tutorial. You now have a basic understanding of the algorithm and a simple C++ implementation. In part 2, we will build upon this foundation to create a more robust and feature-rich implementation, including handling arrival times and calculating performance metrics more accurately. Stay tuned.